Bismillahirrahmanirrahim. So today we are going to start chapter number 4, the title of which is Imperfections in the Atomic and Ionic Arrangement. In simple terms, we can say the imperfections or defects or disruptions in the structure of the material. So in chapter number 3, when we are studying about crystal structure, we assume that they were perfect in nature. The number of atoms were supposed to be, in right number. But in reality, uh, materials are not perfect. They have imperfections. Sometimes the atoms are missing, sometimes there are extra atoms, sometimes there are impurities. So in this chapter, we will talk about these imperfections in detail. So the objectives of this chapter is to introduce the students to the three basic types of imperfections: point defects, line defects, and surface defects, and explore the nature and effects of different types of defects. So this is the chapter outline: point defects, other point defects, dislocations, observing dislocations, significance of dislocations, Schmidt's law, influence of crystal structure, surface defects, and importance of defects. So if you classify defects on the basis of dimensionality, so we have zero-dimensional defects, which we call point defects. A point has zero dimension. One-dimensional defect, usually called line defects. A line has one dimension. Interfacial defects are two-dimensional defects, and bulk defects or volume defects are three-dimensional defects, because a volume has three dimensions. A surface has two dimensions. So interfacial are actually surface defects. Okay, so what are point defects? Imperfections such as vacancies that are located typically at one, in some cases a few sites in the crystal. So they are actually limited to a lattice site. Extended defects are defects that involve several atoms, ions, or thus occur over a finite volume of the crystalline material, like dislocations, stacking faults, etc. What is vacancy? Vacancy is an atom or an ion missing from its regular crystallographic site. Interstitial defect, a point defect produced when an atom is placed into the crystal at a site that is normally not a lattice point. What is substitutional defect? A point defect produced when an atom is removed from a regular lattice point and replaced with a different atom, usually of a different size. So vacancy is actually the absence of an atom. When an atom is missing from its lattice site, we call it vacancy. Interstitial defect is when the empty space between two atoms is filled by another atom, so we call it interstitial. Substitutional means that the atom at a lattice point has been replaced by another atom, so we call it substitutional. So point defects are localized disruption in irregularity of the lattice. It usually is located on or between lattice sites. So there are two types of point defects: substitutional point impurity and interstitial impurity. So what is substitution impurity? Substitution impurity usually occupies normal lattice site. It can be in a form of a dopant. Dopant is something that is deliberately, it is a kind of, dopant is a kind of impurity which is deliberately added to a material. Carbon in iron. When you add carbon in iron, so you get steel. So we deliberately add carbon in iron. So dopant are usually desired impurity, the impurity that you want in the material. Whereas on the other hand, contaminants are the impurities which you do not want in the material and you want to purify it. You want to remove those contaminants. So dopant are desirable impurities. So that's why I have made a smiley face. And contaminant are undesirable impurity. So that's why I have made a frowny face. Allying elements are also kind of a dopants because we alloying is actually adding deliberate impurities inside a host material. Interstitial impurity, when we will talk about this in detail in the later slides. So interstitial is actually the empty space between two lattice sites. So when an atom occupies the empty space between two lattice sites, so that is called interstitial atom or interstitial site. That site is called interstitial site, and the atom occupying that interstitial site is called interstitial atom. So it occupies position between lattice site. Allying elements are like carbon in iron, and because carbon usually occupies interstitial site because carbon is too small an atom in size, whereas iron is big in size. Contaminants are, hydrogen in iron. So we want to remove hydrogen from iron. So these are the different depictions. If you look at figure A, so an atom was supposed to be here. This is the latest site, but it is missing. So it's a vacancy. And because of this, the absence of this atom, the whole structure is distorted. If you look at B, so this dark atom, I'm talking about this atom, is occupying a space between lattice site. So it has pushed around the atoms around this interstitial site. So this is interstitial atom. This black atom is interstitial atom. It is occupying the site between the lattice sites. If you look at C, so this black atom, it is actually it has replaced a light blue atom. A light blue atom was supposed to be here, but this black atom has replaced that atom. So because of the difference in size, this dark atom is smaller in size than the blue atom. So this structure has been distorted because of the smaller size of the black atom. So this is a substitutional replacement, right? Or substitutional atom because it has replaced an existing atom. Whereas in B, this dark or black atom has not replaced any atom. All the blue atoms in number are complete in number, but this black atom is an additional atom which has occupied an empty space in between the blue atoms. If you look at D, so a larger size foreign atom has occupied a lattice site. It has replaced a blue atom, but because this gray atom is bigger in size, so it has pushed the surrounding atoms outward. In C, this black atom is smaller in size, so the surrounding outer, atoms are pushing inwards in this direction. Whereas here, the surrounded atoms have been pushed in outer direction. If you look at E, so E is actually Frankel defect. So what is Frankel defect? When, it is usually for ionic material in which you have ion pairs, a cation and an anion. So if you look at this cation, so what happens is it was supposed to be here, but it has moved here. So it has produced a vacancy here and an interstitial here. So overall, the overall charge balance is neutral because the atom has not ejected or left this material. It is inside this material, but a localized charge disruption has happened. So we call it Frankel defect. When an ion moves from its place and moves to another place. So we call it Frankel defect. If you look at F, so this defect is called Schottky defect because an ion pair is missing, right? An anion is missing from here and a cation is missing from here. So an ion pair is missing. So the last two are usually related to ionic material because it involves ion pairs. Frankel defect can also be related to metals as well or non-ionic material as well. But Schottky is related to ionic material. All of these defects disrupt the perfect arrangement of the surrounding atoms. So how are point defects caused in a material? It may be introduced by movement of atoms or ions. When they gain energy by heating, when you heat the material, the atom moves around. So these point defects can occur inside the material. During processing of the material, when you are putting or exerting force on the material, just like when you're cutting a material or you're forging a material or you're bending a material or you're stretching a material. So these forces actually make the atoms of the material move around, and that movement can also result in these defects, these point defects. And the third cause can be by introduction of other atoms if you add impurities into the material. So it can also cause point defects. So there are three main causes: heating, processing, and introduction of impurities. So now let's talk about the effect of temperature on vacancy concentration. So here is an example. Calculate the concentration of vacancies in copper at room temperature, 25 degrees centigrade. What temperature will be needed to heat treat copper such that the concentration of vacancies produced will be 1,000 times more than the equilibrium concentration of vacancies at room temperature? Assume that 20,000 calories are required to produce a mole of vacancies in copper. So we know that copper is FCC, phase center cubic, and its latest parameter is 0.36195, 0.36151 nanometer. The basis is 1. Therefore, basis means the number of atoms per lattice site. How many atoms are associated with a lattice site is called basis. So therefore, the number of copper atoms or lattice points per cubic centimeter is N is equal to 4 atoms per unit cell. We know that from chapter number 3 that there are 4 atoms in an FCC cell, unit cell, divided by the lattice parameter of the copper unit cell in centimeters. So when you do 4 divided by 3.6151 multiplied 10 raised to the power minus 8 cubic centimeter, so you get 8.47 multiplied by 10 raised to the power 22. 10 raised to the power 22 copper atoms per cubic centimeter. So now at room temperature, we have the temperature given was 25 degrees centigrade. So we have to convert it into Kelvin. So it will be 298 Kelvin. So number of vacancies is equal to N exponent of QV divided by RT. So where NV is the number of vacancies per cubic centimeter, N is the number of atoms per cubic centimeter, QV is the energy required to produce 1 mole of vacancies in calorie per mole or joules per mole. These are the units of QV. R is the gas constant, which is 1.987 calories per mole Kelvin or 8.31 joules per mole Kelvin. And T is the temperature in Kelvin. So if you put the data in this formula, we have determined the number of atoms per cubic centimeter, which was 8.47 multiplied 10 to the power 22 from previous slide. And the QV value is given, which is 20,000 calories per mole. The gas constant is also given, and the temperature is room temperature, which is 298 Kelvin. So the result is 1.815 multiplied 10 to the power 8 vacancies per cubic centimeter. Now, these are the number of vacancies per cubic centimeter at, equilibrium. This is the equilibrium concentration of vacancies at room temperature. What the problem wants is 1,000 times more. So what we need to do is we need to multiply this value by 1,000 because we need 1,000 times more vacancies, and then solve this equation for T, right? So the number of vacancies will be this multiplied by 1,000. The vacancies that we determined, multiply by 1,000. So this will be the number of vacancies, and we also have N, we have Q, we have R, and we will solve it for T. So when you do that, the temperature turns out to be 102 degree centigrade. So if you want to have 1,000 times more vacancies from the equilibrium room temperature, you need to raise the temperature to 102 degree centigrade from 25 degree centigrade. So then by raising the temperature from 25 degree centigrade to 102 degree centigrade, the number of vacancies will get 1,000 times more. So this is another example. Determine the number of vacancies needed for a BCC iron crystal to have a density of 7.87 gram per cubic centimeter. The latest parameter of the iron is 2.866 multiplied 10 raised to the power minus 8 centimeter. Now, because because the definition of vacancy is the absence of atoms. Now, if the atom is absent, it means that the mass is absent, right? And when mass is absent, it means that the density will be lower. So if a material have more vacancies, it means that its density will be lower because the mass is low. So what we need to do in this problem is that we need to find out the density of a perfect material if the number of atoms are complete, right? So what will be the density of iron if there are no vacancies? So for that, we have a formula from chapter number 3, which is the density of the material, or the material can be found by the number of atoms per unit cell multiplied by the molecular mass divided by the volume of the unit cell divided by the Avogadro number. So because iron is BCC, so there are 2 atoms per unit cell multiplied by 55.847 gram per mole, which is the molecular weight of iron, divided by the latest parameter, the cube of latest parameter. So it will give you the volume of the unit cell. So 2.866 multiplied 10 raised to the power minus 8 power 3, right? And divided by the Avogadro number, which is 6.02 multiplied 10 raised to the power 23 atoms per mole. So the density of the perfect structured iron is 7.8814 gram per cubic centimeter. So this can be termed as the theoretical density of iron. Now, the iron that we have on our hand in the problem has a density of 7.87 gram per cubic centimeter. So there is a difference of 0.01 gram per cubic centimeter in the density. So what we need to do is we need to find out how many atoms are missing, or how many vacancies are there in this iron, right? Because if you make the vacancy 0, which means that the number of atoms in the iron are complete, so the density should have been 7.8814 gram per cubic centimeter. So what we need to do is we need to solve this problem for the number of atoms per unit cell, because we do have the density, so we do have the molecular mass, we do have the volume, we do have the Avogadro number. We will solve it for the number of atoms per unit cell. So when you do that, so the number of atoms per unit cell turns out to be 1.9971. So which is less than 2. For BCC, it should have been 2, but here it is 1.9971. So this is the average number of atoms per unit cell. It does not mean that the atom has been divided, right, into components. It means that some unit cells has 2 atoms per unit cell, whereas some unit cell has 1 atom per unit cell. Okay, so there should be 2 minus 1.991, 0.0029 vacancies per unit cell, right? There are 0.0029 vacancies per unit cell. So the number of vacancies per cubic centimeter is 0.0029 divided by 2.866 multiplied 10 to the power minus 8 cubic centimeter. So it turns out to be 1.23 multiplied 10 to the power 20 vacancies per cubic centimeter. So this is example number 4.3, which is sites for carbon in iron. Where do the carbon reside in iron? When you add carbon into iron, so where does it, what sites or which location does it occupy? What location the carbon occupies inside the iron structure? So the problem is in FCC iron, carbon atoms are located at octahedral sites at the center of each edge of the unit cell, right? 1 by 2, 0, 0. And at the center of the unit cell, half, half, half. In BCC iron, carbon atoms enter tetrahedral sites such as 1 by 4, 1 by 2, 0. Now, if you look at this problem, so they are called, they're saying FCC iron, and then in the second line, they are saying BCC iron. So what happens is that the structure of the material changes with temperature, right? When the iron is at room temperature, so it is in BCC shape or BCC structure. When you raise the temperature of iron to a certain level, above 700 degrees centigrade, so the iron turns to FCC structure, right? So this phenomena is called polymorphism, right? When the structure of the material changes with temperature. Okay, so when an iron is FCC, when the structure of the iron is FCC, the carbon atoms occupy this site in the unit cell, half, 0, 0, and half, half, half. In BCC, when the iron is in BCC form, the carbon atoms occupies this site, 1 by 4, 1 by 2, 0, right? So the latest parameter is 0.3571 nanometer for FCC iron and 0.2866 nanometer for BCC iron. Assume that carbon atoms have a radius of 0.071 nanometer. What would we expect a greater distortion of the crystal by an interstitial carbon atom in FCC or BCC iron? So what they are asking is the distortion level or the amount of distortion in FCC and BCC. What would be the atomic percentage of carbon in each type of iron if all the interstitial sites were filled? If all the empty spaces between latest sites were filled, how much carbon in terms of atomic percentage can we add to the iron in each form, in BCC form and in FCC form? So if you look at these sites, these spaces, they have given it names like tetrahedral site, right? Octahedral site. So if you look at this slide, so we give names to these empty spaces on the basis of the surrounding atoms that this atom is going to touch, right? So if you look at this atom, this gray atom in this figure, so this gray atom is going to touch this atom, this atom, and the 4 in the bottom plane. So it means that this center atom is going to touch 8 atoms in the surrounding. So when the interstitial atom touch 8 atoms in the surrounding, so we call it cubic site. What do we call it? We call it cubic site. When the interstitial atom touches 4 atoms, 1, 2, 3, 4. So the site is called tetrahedral. Tetra means 4. Hedral means sides. So if you draw a polygon around this site, you will end up with a 4-sided polygon. Okay. If you look at this site, which is half, what side is this? This is half in x-axis. You have to come half in x-axis, then half in y-axis, and half in z-axis. If you look at this side, so you have to come, if this is your 0, this atom is your 0, so you have to come one lattice site or one lattice perimeter in x-axis, half in y, and 1/4 in z-axis. So you will reach this site. If you look at this side, so you have to move half in x-axis, half lattice perimeter in x-axis, one full lattice perimeter in y-axis, and half in z-axis. So you will reach this site. So half, 1, half. And why do we call it octahedral? We call it octahedral because this atom is going to touch these 4 atoms in this plane, and this atom and the atom here, which is, if you extend this unit cell like this, so there is going to be an atom in the middle here as well, which is going to be touched by this atom. So how many atoms does this interstitial atom touch? 1, 2, 3, 4, 5, 6. 4 in the same plane, 1 behind and 1 in front. So if you draw a polygon connecting all these surrounding atoms, you are going to end up with an 8-sided body. 8, E-I-G-H-T. 8-sided body, right? It's going to look like this. Right? Okay, so we call it octahedral. Octa means 8. Octa means 8. And hedral means side. So if you look at FCC, so we have these sides as octahedral sides and this side as tetrahedral side. Okay, so in this problem, they are talking about these sides. Okay, now if you take this 100 phase, right? So which one is 100 phase? If I draw a unit cell, so this side is the 100 phase. So if you look at the 100 phase, so you're going to find an atom here, here, and here, which are these atoms, these 4 atoms, and an interstitial here, right? So which is this atom, light blue atom with small r. Okay, so this side of the the side of the unit cell is equal to A. So because this interstitial atom is in the middle, so this is half A, right? And because it is 1/4 on 1/4, so this side is going to be 1/4 A, right? So this is a triangle, right? And by applying simple trigonometric rules, you can find out the atomic radius as well, right? So what they are saying is the location of 1/4, 1/2 interstitial site in BCC metal is showing the arrangement of the normal atoms and interstitial site. So A is showing the location of 1/4, 1/2 interstitial site in BCC metal, whereas B is showing the half 00 site in FCC metal, right? So this is FCC. this B is FCC, right? So these are the interstitial atom, the atom in between the lattice sites. C is the H center and cube center. H center and cube center are some of the interstitial sites in FCC structure. You know, this is the H center and this is the cube center. Okay, we could calculate the size of the interstitial site. We need to find out the empty space between the lattice site, right? So the size of the interstitial site at the 1/4, 1/20 location with the help of figure 4.2a. The radius RBCC of the iron atom is under root 3a divided by 4. If you remember the formula of packing factor and packing fraction, you would know, you could find out this formula. So the radius of BCC iron is under root 3a divided by 4, which is equal to under root 3 into the latest parameter of iron divided by 4 is 0.121 nanometer, right? From figure 4.2a, we find that this distance, this hypotenuse, is the radius of iron atom plus radius of carbon atom. So you know radius of interstitial is actually the radius of carbon atom plus radius of iron atom. So if you apply Pythagoras theorem, so the square of this is equal to the sum of the square of this side and this side, right? So that is 1/2a plus 1/4a. You know, the square of 1/2a plus the square of 1/4a is equal to hypotenuse, which is actually the radius of the smaller atom plus the radius of the bigger atom. So if you solve it for, we know the radius of the bigger atom, which in this case is iron, we can solve it for the radius of the interstitial. So it would turn out to be 0.0361 nanometer. For FCC iron, the interstitial sites such as the 1/200 lies along 100 directions. Thus, the radius of the iron atom and the radius of the interstitial site are, the radius of the FCC. We did, this was for BCC. Now we are going to do it for FCC. So the radius of FCC is under root 2a divided by 4. So that is 0.1263 nanometer. And if you look at this figure, right? So this length is A0. So this is capital R, this is capital R, and this is small 2r. So A0 is equal to 2 capital R plus 2 small r. So, they have done the same here, right? So you can solve it for interstitial and you will get 0.0522 nanometer. So the interstitial site in the BCC iron is smaller than the interstitial site in the FCC iron. Although both are smaller than the carbon atom, carbon distorts the BCC crystal structure more than the FCC structure. Why? Because the space in the BCC structure is smaller and the carbon atom is comparatively bigger than that space. So when you put a big atom into a small space, it's going to create more distortion than if you put it in a bigger space. So because the space in the BCC is smaller, that's why it will produce more distortion in BCC than the distortion that it would create in FCC, because the space in FCC is slightly bigger than the space in BCC. As a result, fewer carbon atoms are expected to enter interstitial positions in BCC iron than in FCC iron. So which means that more carbon is going to go into FCC iron than BCC iron. Okay, we can find out the atomic percentage as well. So we can find a total of 24 interstitial sites of the type 1/4, 1/20. However, since each site is located at a face of the unit cell, only half of each site belongs uniquely to a single cell. Because if this, if you're talking about this face, 1/4, 1/20. So which one was 1/4, 1/20? So this one, right? So this is actually the face, it is somewhere like here. So this is half in this unit cell and half in the attached adjacent unit cell. So because the total number is 24 and half of them are in this unit cell, so it will be 12. So the atomic percentage would be 12 carbon atoms divided by 12 carbon atoms plus 2 iron atoms. So that would be 86% carbon can be added to iron in BCC. Whereas in FCC, the same turns out to be 50%, right? But in reality, these percentages are very high because in reality, we do not add more than 2% or 1.5% or even 1% of carbon in iron. A normal steel that we usually use in our buildings has 0.8% carbon at most. Okay, so what are the other point defects? So interstitiality, a point defect caused when a normal atom occupies an interstitial site in the crystal. So we call it interstitiality. Frankel defect is a pair of point defects produced when an ion moves to create an interstitial site. We talked about this, right? When an ion moves from its position or an atom moves from its supposed position to another position. Schottky defect is the when an iron pair is ion pair is missing. And Kruger-Wink notation is used to show the a system used to indicate point defects in materials. The main body of the notation indicates the type of defect or the element involved. So if you look at this figure, a divalent cation replaces, a double positive charge ion moves in. So two cation have to move out in order to restore charge balance, right? So one cation has moved in and a cation which was here has moved out and a cation from here has moved out. So we have a net vacancy, but the charge balance has been kept restored. Okay, so application of the Kruger-Wink notation. So, okay. So for Kruger-Wink notation, we need to keep in mind some rules, and those rules are that charge balance must be maintained, right? Mass balance must be maintained, and crystallographic sites must be conserved. So these are the three rules, the underlying three rules for Kruger-Wink notation. Okay, so when the appropriate defect reactions for incorporation of magnesium oxide, write the appropriate defect reaction for number 1, incorporation of magnesium oxide in the nickel oxide, and 2, formation of a Schottky defect in alumina. So MgO is the guest and NiO is the host material. We are adding MgO into NiO. So this is guest and this is the host. We will assume that Mg plus 2 ions will occupy Ni plus 2 sites, and oxygen anions from MgO will occupy O minus 2 sites. So if you look at this, MgO is going to come into NiO, and Mg is going to replace Ni, and oxygen is going to replace oxygen. So because the valence of both the host atom and the guest atom and the host atom is the same, so it is going to result in neutrality, right? So X stands for neutral. Clear? Okay. For 2, Schottky defect means an ion pair is missing. So thus we're talking about alumina, so which means that one aluminum atom is missing. Aluminum atom is missing and oxygen atom is missing. So null means vacancy, right? So a vacancy has been produced in alumina by aluminum is Al plus 3. So when an aluminum gets out, so it's going to result in minus 3. Why? Because plus 3 has gone out. So the resultant charge on the material will be minus 3. When oxygen leaves, so oxygen is minus 2. So the resultant charge on the material will be plus 2. So a charge balance must remain balanced, right? So this is when one aluminum atom goes out and one oxygen atom goes out. So aluminum will create a minus 3 net charge on the material. Oxygen will create a plus 2 net charge on the material. So if you add these two, so you will have a minus 1 net charge in the material, which is against the rule of the Kruger-Wink notation. So what we need to do is we need to balance it out. So these bars actually donate negative, and these dot actually denote positive. So when an aluminum goes out, so it is going to create a negative 3 charge, and when oxygen goes out, it's going to create a positive 2 charge. So in order to restore balance, so what we need to do is we need to have 2 aluminum atom leaving the material and 3 oxygen atoms. So it will 2 into 3 will be minus 6 and 3 into 2 will be plus 6. So the resultant charge will be 0. So this is how you use Kruger-Wink notation. So we are going to do another example on this too. So write the appropriate defect reaction for the incorporation of calcium oxide in zirconia using the Kruger-Wink notation. We will assume that Ca plus 2 will occupy zirconium plus 4 sites. If we send one calcium ion into to zirconium site, the site will have effective negative charge of minus 2. Why? Because a plus 4 will leave, which will create a minus 4 charge, and a plus 2 will enter. So the remaining resultant charge will be minus 2. Okay, we have used one zirconium site, and site balance would require us to utilize 2 oxygen sites. We can send one oxygen from CaO to one of the O oxygen sites in zirconia. The other oxygen site must be used, and since mass balance must also be maintained, we will have to keep this site vacant. So what will happen is calcium oxide is coming into the zirconia, and a negative double charge is going to get created when calcium replaces the zirconium ion. Okay, and oxygen is going to replace oxygen, so it will remain neutral. The charge will cancel each other out, and then we will have to create a vacancy. We have to remove one oxygen, in order to balance these two, this double negative charge, right? So this will get balanced. Okay, thank you. This was point defects. In the next lecture, we are going to talk about line defects.